Good afternoon. Hello.
Good afternoon.
How are you guys? Who is this? This is Andres. Andres, am I butchering your name or that's pretty
No,
okay?
it's pretty good. You're pronouncing it right.
Okay. You're not just being nice to me, right? Right.
No, I'm not.
Yeah, cool. Hi Andres. Hi Devon. Hi Adil. Hi Carla with a K. Hi Danward. Sebastian. Isaac. Ray. Who else is there? Feng. Gauli, Cheyenne, Cheyenne. Where is that name from? It's a pretty cool name. Yasmin, Varun, Roxana. Sounds very rock music-ish. Eleanor, Said. All right, infrared spectroscopy. How are you guys doing? One more day, then weekend. I don't know. Is weekend different for most of you, or weekend is just an extension these days? Weekend is different.
I work weekend, so it's just a work day for me.
Oh, okay. All right. Where do you work, Devon?
I work for a vaccine, like vaccines for dogs and cats at VIP Pet Care.
Oh, okay.
Travel up and down California doing vaccine clinics.
No kidding. Seriously. How
Mm-hmm.
far do you have to drive? What's the farthest you have driven?
Tehachapi, I guess.
Wow. That's
Yeah,
not,
we go.
that's not that bad.
It's like a 3-4 hour drive, depending.
Okay. That's that's not that close. Yeah, yeah. Cool. Anybody else? Weekend is better or weekend is less work or more work? What is it? Any Hi Arshnur, Amela, Helena. I'm just reading your names. Kind of bored. I'm not bored. This is my third class today. Tuesdays and Thursdays are really busy. The only symptom I have is what? I have to really read the whatever you guys are writing on the chat. Sleeping randomly and for long periods. That's funny. You guys have good sense of humor. We can just be crying over homework. Come on, there is no homework. That's good. How you feeling? I had it last year. What? Halfway caught COVID. Oh, that's not good. How bad is it, Cheyenne? Are you okay? Where is Cheyenne on the screen? Right there, on the right side of my screen. Hope you haven't given it to your parents and other people in the family. Are you the culprit? Did you have a party with your buddies in your fraternity or something? Is that how you got it, Cheyenne?
No, my brother's the
Culprit?
he's the lead COVID expert in Fresno.
Ah, is that sarcasm or he's a physician or something or
He
he's?
works at St. Agnes. I was helping him out
I'm sorry.
his gear and stuff, and
Oh,
I touched him. Yeah, I'm all right though. Just super tired all the time.
I'm sorry. Yeah, take your time. Is that your home or is that your dorm? No, that cannot be dorm. That's your.
That's my apartment.
Yeah, okay. All right, let's talk about infrared spectroscopy, IR. Okay, I'm gonna switch here. Keep your cameras on, man, people, ladies and gentlemen. That'll keep me awake. Okay, and you'll get 2 bonus points at the end. So there is a carrot. You know, you can like stay still. You will look like a picture if you just freeze yourself like Frozen, like in the movie. Okay, am I recording? Hmm. Yeah, it is recording. Okay, let's go. I have a very ambitious plan today. Um, no pink. Pink got replaced with red. Okay, 128B, 128B, Tuesday, Thursday. Today is 2/4/21. We are talking about IR spectroscopy. Okay. Um, radio wave, microwave, infrared, visible, ultraviolet, X-ray, gamma ray. Okay, so we are infrared light, infrared electro in aerospace, magnetic radiation, okay, or wave or whatever you call it. Okay, electromagnetic radiation is in between microwave and visible. So it's I never thought that it's actually weaker than visible, but it's weaker than visible. So it's weaker than red. Okay. So if you have a molecule, I'm going to just draw a molecule with all kinds of functional groups. Okay. Let's stretch our imagination. Let's draw a molecule. Let's keep this end CH3. Let's put something here. Let's put like a double bond here, and see. Let's make that. Let's make that. This carbon is a little different. Okay, and let's make these hydrogens purple. Okay, what else? Then let's stick. That's not a good sign. Let's put a carbon here. Oxygen and a hydrogen here. Let's put a hydrogen here. Let's put something else. Let's put a nitrogen here. It's an interesting molecule, to say the least. Let's take a nitrogen here, and H. It's getting too crowded. Hold on. NH2. It's the same thing. I just didn't draw the big long bond. Let's put a triple bond here. Okay. Too much erasing. And that's another hydrogen. What are we missing? Oh, we are missing something very important. Hold on. We need to take care of that. And then what I'm going to do is I'm going to draw a C and a carbonyl, and then on the other side we might put like a C oxygen and H. Okay, so I just drew a random molecule with whole bunch of functional groups in them. Okay, so if I ask you some general questions, okay, let's practice functional groups very fast. 5 minutes. This part of the molecule, okay, this part of the molecule, if you just see this, okay, CH3 with no double bonds. This particular carbon is in specific hybridization mode. So how do you call this group? Should you call it an alkynyl group, like a triple bond, alkenyl group on a double bond, or are you going to just call it alkyl group? Should you say it's a carboxylic acid? Should you say it's an amine? What should you say? How should you describe the methyl group, CH3? Anybody? Don't write on the chat because I'm not reading the chat. I'm too far from my screen. How would you call it? What is it?
sp3 alkane carbon.
Alkane carbon, but this group is going to be called
Methyl group?
alkyl, right? It's an alkyl group. So that's sp3. It's important. What kind of hybridization is here? Very fast.
sp2.
SP2.
sp2. What about here?
SP.
sp.
sp, just sp. Okay. What's this whole functional group? This functional groups. C double bond OOH. What is it?
Oh, it's an alkene? Like an alkyne, like with Y?
Alkyne. Sorry, I'm not talking about that. I'm just talking about. Let me see if I can.
Carboxylic acid.
There you go. So don't look at that. Just this carboxylic acid. That's a carboxylic acid. What about this purple group NH2? What is it? What kind of group is
Amine.
that? NH2.
What's amine?
It's an A word.
Amine.
Amine. Okay. There are how many kinds of amines are present? Very fast. Quick.
I think there's 2.
1 degree, 2 degree, 3 degree. What are those? NH2 is what kind of an amine?
Is primary?
Primary. If it were just NH, what kind of amine would that be?
Secondary.
Secondary. If there is no hydrogen, then
Tertiary.
tertiary. Very good. Very good. Awesome. What group is this OH?
Wait.
Alcohol?
Sorry?
Alcohol?
Alcohol. Okay. Alcohol. Do you guys know what kind of alcohol it is based on the number of hydrogens attached to this carbon?
Pentanol?
There can be CH2OH. There can be CHOH, or there can be no hydrogen, just COH. This is
So this is
CHOH.
secondary.
One is primary, one is secondary, one is tertiary. Which one is this?
Secondary.
Secondary. Secondary alcohol, alkynyl group, carboxylic acid, primary amine, an alkene group, and a methyl group. Okay. This would be a perfect pre-NMR discussion, but I'm supposed to be not getting distracted, okay, and not distract you. Okay. So now, if you look at this molecule, and if we think about IR, there are a bunch of different body parts, different springs that this molecule is made out of. You can think about this molecule like, there is a spring here, there is a spring here, there is a spring here, this end. Then from here, this is another spring. Then this is another spring. Okay, and that's another spring. So you can think about this molecule made out of springs. And as you pass infrared radiation through the molecule, they just start doing crazy dance. Okay, stretching and bending. So this is stretching and contracting, stretching and contracting. And all those movements, body movements, when you are dancing, you're burning calories. You're absorbing energy. So those energies are being shown as peaks in the infrared spectrum. In the infrared spectrum. That's all. Okay. So how does an NMR infrared spectrum look like? We have seen it on the PDF. I'm going to just draw a mock infrared spectrum, like my best rendering. How bad is my rectangle? Let's do better. Okay. Let's say this is an infrared spectrum. One is spectrum. You guys better get used to it and correct it, because I'm very finicky and I'm very particular about it. I don't like when someone says, I have 2 spectrum or spectrums. Spectrums is wrong. 2 spectrum is also wrong. 2 spectra and 1 spectrum. Okay. Infrared spectrum. Okay. You know what? Let me just move this guy down a little bit. Okay. I'm trying to be clever today for once to cover a lot of materials using some pictorial methodology. So infrared spectrum, 1 spectrum, multiple spectra. The x-axis is an axis of energy. Okay, the x-axis, okay, that it's an axis of frequency. And the frequency is wave number. Okay. Nu bar. Nu bar means number of waves per centimeter. So this is per centimeter, centimeter inverse. A number per centimeter inverse. The extreme right is less energy. As you go left, it's more energy. Okay, got it? So the extreme right, that number usually for IR spectrum is 400. Okay, 400 centimeter inverse. So whenever, if I'm asking you, what's the range of infrared absorption peak for a C double bond C, you should write down the range and you should always specify what that unit is. You should always say 3000, less than 3000 centimeter inverse. You should say 1600 to 1800 centimeter inverse. If you don't write the centimeter inverse, I'm going to take 1 point out. So I'm not trying to be mean. I'm just saying that this is my expectation. Okay. The extreme right is 400. Extreme left is 4000 centimeter inverse. I'm going to just write down centimeter inverse one more time. I know that this is probably where the camera cuts off. I think we can still see it. Yeah. Okay. So we're good.
The quiz and the test for the question, will it be like multiple choice or will we have to fill it out like we did for the practice?
It will be multiple choice and a combination of non-multiple choice descriptive. So I haven't figured it out yet.
So the ones we send in, just make sure we do it how you said.
As long as you know the material, you will come out fine.
All right.
Okay. All right. So so that's the x-axis. And a nu bar, the Greek letter nu and with a bar on top of it, that's described as that's describing wave number of waves per second. 400 centimeter inverse is on the extreme right. That's a smaller number, that means less powerful. 400 waves per centimeter and 4000 waves per centimeter on the other side, on the left side. Okay, so this is much more powerful. The y-axis, there it's described in two different ways. Okay, you need to know that. So I want you to know that. I want you to know what IR stands for, not I am or you are. It's IR. It's wrong, bad grammar. I'm just kidding. That was a silly joke. Okay, if you're wondering, like, what is he talking about? That y-axis is either where do I write it? Maybe here. It's percent transmission. Percent transmission or percent absorbance. Absorption. Percent absorbance or absorption. Okay, what does that mean? Okay, let's say you have a cuvette, like a little special glass made, quartz made container, like a little vial, but it's square. Okay, it's not round, it's square, or it has some shape. Okay, let's say you have that. Okay, this is where you keep your sample, IR sample. You put this compound in here inside, and you put some solvent or whatever. Okay, in the older days, you had to do all kinds of funny business, and actually these days the infrared spectrometer that we have, all you have to do is, you don't even have to do this. There is a plate and there is a spot. All you have to do is either you take the powder solid or a drop of that liquid pure. You don't mix it with something. You can mix it. You can actually make a solution in some solvents. You put it down here as a little droplet. Okay, you drop it here. Then you have a probe and you set the machine up, and then you basically pass infrared light through it, varying the wavelength, right? Varying the wavelength. Okay, Let me ask you a question. This could be so you need to really understand the concept to do well in my exams. Okay. Let me ask you a question. 4,000 centimeter inverse. Oops. 400 centimeter inverse. Okay. Number of waves per centimeter. What unit is that? Is it a unit of wavelength or is it a unit of frequency? What have you learned so far?
I think it's a unity. Wavelength is. I think it's a.
It's frequency.
It's frequency. Anybody else wants to join in agree with her or not agree with her?
I agree with frequency as well.
Okay. Frequency and energy, are they directly proportional or they're inversely proportional? More frequency, more energy, or more frequency, less energy?
Directly proportional?
Directly proportional.
Frequency means you have higher energy.
Higher frequency means higher energy. On the extreme right, for this wavelength, for this frequency of infrared spectrum, infrared radiation, 400 centimeter inverse, 400 waves per centimeter and 4,000 waves per centimeter. Which end has higher wavelength? The right end, that's this infrared radiation, or this infrared radiation? Which one has higher wavelength?
The right end with the 400 centimeters
Inverse?
per inverse.
Does everybody agree with her or no?
Yes.
Okay, good. I'm just checking. Okay. Percentage absorption means as the infrared radiation is passing through it, right? Let's say I'm just going to pretend that it's passing through from the top to bottom. Okay. So that's the sample. Let's say after that, you're passing infrared radiation this way, okay? By changing the wavelength. You're going from very high wavelength to like low wavelength, and you're scanning the entire spectrum of that infrared radiation, 400 to 4,000, and see what gets absorbed and what doesn't get absorbed, right? So as you're decreasing radiation wavelength, and as you're increasing the frequency, okay, what goes into the sample and what comes out, the entering and exiting IR. So there is some absorption going on, right? So whatever absorption is going on, that represents that part of the molecule for doing the dance here, it's absorbing here. For doing the dance here, it's absorbing this range. For doing the dance here, it's absorbing here. For doing the dance here, it's absorbing here, something like that. So different ranges of infrared radiation is being absorbed to excite that particular spring, and it's quantized. Only certain ranges of infrared radiation will be utilized to excite certain parts of the molecule. Okay, that's different from that. That's different from that. This is different from that. The carbonyl is different. The CC bond is different. The NH is different, and they have the shapes, densities, and other properties and the location. Okay. This is percentage absorption and percentage transmission. Percentage transmission means how much is getting out of it. And this means how much is actually getting absorbed. So let me ask you a funny question. I don't think the book will ever talk about this. If you take an IR spectrum, and if you see the spectrum like this, okay, you get a spectrum. Okay, you get a spectrum. I'm just going to draw like a mock spectrum. Let's say this is an IR spectrum. Okay, whatever 4,000 on the left, and 400 on the right. And the spectrum that's written in red in this purple colored business this is your spectrum. You see a line on the very top end of the spectrum. What does it mean as far as absorption or transmission is concerned? What do you think? When you get a line on the top like this, the red line or on the blue line, what does it mean?
That you're basically getting just pure light, or it's just
What went in and what came out? Are they everything got absorbed or nothing got absorbed?
nothing got absorbed.
Nothing got absorbed. So the percentage absorption, if you see a line on the top, that's 0% absorption. So this range, this is 0, and this down here is 100. Okay? So 0% got absorbed, 100% got absorbed. If you see a line down here for the spectrum, if your spectrum, I can just cheat. If your spectrum looks like this, actually the line is down here, that means every darn frequency between 400 and 4000 got absorbed to the fullest. Okay, you have this strange, weird molecule that absorbed every frequency of IR to the same, range, same intensity, same percentage. So you got a flat line at the very bottom. Okay, so if you see a line like that, that means nothing got absorbed. Nothing got absorbed means everything got transmitted. Okay, so this down here, this is 0% transmission, this is 100% transmission, 0% absorption, 100% absorption. And they're going to be all relative. Everything is going to be normalized with respect to the tallest peak. If you have one peak that's about this big, then everything else is going to be adjusted according with respect to that. Okay, that's how the spectrum looks like. And the spectrum could look like a bunch of different peaks. So as the infrared beam starts scanning through the different frequencies, okay, so this is how the spectrum might look like in reality. This was an extreme case. I don't think you will ever see anything like that. So let's say you go in there and then something gets absorbed, then something like a broad peak, then maybe a peak here, then maybe a peak here, then maybe a peak here, a tall peak, and maybe a peak here, maybe something here, maybe there is a broad peak here, something like that. So this is how it looks like. Okay, this is how an IR spectrum looks like. So what do you have to know for the sake of the quiz? I want you to know the x-axis, the unit, the range. I want you to know what's along the y-axis. What does percent absorption and percent transmittance mean? Sometimes when we use our infrared spectrometer and it's in absorption or transmittance and it starts to look really crazy, all you have to do is go back and select the other one. Okay, I think we usually have it set for transmittance probably. Okay, this means that nothing got absorbed, something got absorbed, a little more, then that absorption is getting done. So from whatever this range is, this is the range of that particular peak. Whichever spring is being excited by that energy of IR, okay, that's the range. Like let's say 400 to 420 centimeter inverse. This may be 1000 to 1150 centimeter inverse. This guy may be 1680 to 1710 centimeter inverse. This guy may be 3200 to 3600 centimeter inverse. This particular peak might be, I don't know, 3050 to 3095 centimeter inverse, something like that. Okay. So this is how you read an IR spectrum. This is what the IR spectrum will look like. Okay. So I'm going to take a pause. There's not a lot to like study or understand. There is not a lot of concepts going on in infrared spectroscopy. After this, it's going to be pretty boring. I'm going to just list a certain ranges, frequency ranges for absorptions for different body parts, different functional groups, and I want you to kind of remember that. Okay, this region 600 or 400 to like I don't know what's the number, 400 to 1,000 or something like that. That's called fingerprint. It's very telling. I'm making a confession right now. I'm pretty bad at it. So I'm probably not going to be bothering about it a lot. Okay. I'm just going to talk about certain, and a lot of bending happens here. If a molecule, if a certain bond is bending, those things get absorbed in the 400 to 1,000 range, centimeter inverse. And it can be really crowded, and you really have to have a really awesome eye to make sense out of it, to decipher all the data that's stored in there. I'm not that good with IR. My wife is, and other people are. So, if you're taking this course from them, then you probably get a better insight of that. I'm just making a confession that I'm more excited about NMR, but I'm kind of a little weak on, especially on the right side of the IR. Okay, I'm okay here. Okay, so we're going to spend more time specifying certain peaks, certain absorption, certain functional groups from 1,000 to the other end, 4,000. Okay, take a look at the spectrum. We haven't really talked a lot about infrared spectroscopy yet. This is pretty straightforward. We also have the PowerPoint to fall back on, 2 PowerPoints actually. We will probably refer back to the PowerPoint maybe once or twice. Okay, so and then I'm going to start listing different functional groups and where do they show up. Okay, so I'm going to clean up the board, and then we will probably start giving you some numbers. Take a look at the board. I think I might take a picture because I'm going to start erasing a few things. I'm going to stand right in front of the camera, so excuse me. I beg your pardon. There you go. You get the general idea, right? It's pretty straightforward. I'm not going to ask you a question right now. Ask you to ask me a question. Let's keep going. Okay. There's not a whole lot to discuss at this point. So we need board space. Okay. I'll tell you like what are the peaks, what are the infrared infrared radiation, like spectroscopy related peaks that I want you to remember. I'm hoping that eventually you guys will be able to, I don't know if you have taken 129. Well, it's probably too late. I don't know what's the situation is going to be in the summer, but if you ever go back to a lab, or if you do research, if you go for master's or PhD or medical school or somewhere, and I don't know, maybe you're using infrared spectroscopy, maybe this knowledge can be helpful. I have no idea where IR can be useful, but who knows? Who knows? You never know how life works for us. You plan for something and it doesn't work out. Something else happens. Okay. So now I'm going to start listing numbers. Okay. Then I'm going to go back to the PDF and show you, share screen and show you some spectrum and show them like where do they show up. Okay. So what I'm going to do is I'm going to draw like a big rectangle, and I'll start using it for describing different types of peaks. Okay, so let me see if I can draw like a decent rectangle. And bigger the rectangle, better it is. So let's say this is your, not bad, this is your IR spectrum. Okay, x-axis is what color? How about purple? Let's say it's wave number, new bar. extreme right, 400 centimeter inverse, extreme left, 4,000 centimeter inverse. I'm just going to say percent transmission. And this is 100% transmission, 0% transmission. Yeah. 100% absorption, that means everything is getting absorbed. This is nothing is getting absorbed, 100% transmission. Okay. Let's start with the laundry list. It's very exciting. Okay, it's something that I've been looking forward to. Read sarcasm. Okay. I'm gonna draw like write down the laundry list of different peaks. First, CH absorption, carbon hydrogen bond stretching absorption, when it's stretching and contracting. Okay, CH. CH can be of 3 different kinds. What am I talking about? How can CH be 3 different kinds of CHs? How can that vary?
Depends on the hybridization.
Thank you, Varun. One could be sp3ch. So I'm going to try to save time. sp3 carbon hydrogen stretch. That's, you need to really stress that it's a stretch. It's not a bend. It's this business that's absorbing that energy. sp3ch stretch. Unless I mention bend, know that it's a stretch. sp3ch stretch will be less than right below 3,000 centimeter inverse. So let me just see if I can kind of make some sense. So if this is 400 and this is 4,000, let's say this is 3,500. This is I don't know. Let's draw some numbers. I'm just going to randomly draw it. So 1,600, 1,800. Let's say this is 1,000 and this is 1,200. It's the scale is all screwed up. So forgive me for that. I don't have the patience to figure it out right now. So let's say this is 1,000. You know what? I should have probably lowered that top line a little bit so that I can write the numbers above. I don't want to mess with it inside. Okay. Okay. Let's say this is 4,000. Let's say this is 3,500. Let's say this region is 3,000. Forgive me for the terrible scale. 3,000. Yeah, okay, I hear you. 3,500, 4,000. Let's say this is 2,000. Let's say this is 2,300. It's important because we're going to be using those numbers. Let's say this is 1,800. This is 1,600. And this is 1,200. And this is 1,000. 1,000, 1,600, 1,800, 2,000, 2,000, 2,200, 2,300, sorry. Let me see if I can make them a little more visible. 2,300, that's 2,000, this guy. That's 1,800, sorry. That's 1,600. This is 2,000, 1,200, this is 1,000. That's 3,000, 3,500, 4,000, okay? So sp3ch usually absorbs stretching, and sp3ch and contracting will absorb over here. Okay? That guy will absorb here. Something like that. It does not always look as pretty as I will be drawing as a model in an IR spectrum. Okay, it might be not so big, it might be smaller than that, and it could be like a bunch of peaks, because if you look at an alkyl chain, there are a bunch of different CHs. So all of the CH stretches will be showing up at different regions, but in that tiny range, right near at 3000. But it's going to be, this is very important. This is extremely important. These peaks are going to be on the right side of the 3000 mark. If that's the 3000 mark, and if you do not have a double bond or a triple bond, there is absolutely no way you can have a peak on this side greater than 3000. It has to be less than 3000 centimeter inverse. So if you do not see a peak here, you can be rest assured that you have no double bond, you have no single bond, no triple bond. Take it with a pinch of salt, because what I just said is not entirely correct. There are exceptions, okay, for the most part, okay? So if you see the peak on the right side of the 3000 line, then it's sp3ch. What's the intensity? Whether it's going to be sharp or broad, it's going to be a sharp peak. Okay, intensity will be moderate to intense. M moderate, I intense, W weak, so that we save some space. Okay, that's that. sp2ch. It's something like this. I'm just going to draw it and then I'm going to erase it. sp3ch will be an example. Our favorite alcohol. Okay. How many types of CHs are there? Let me see how you understand symmetry. How many types of CH bonds are present in ethanol? And let's answer that.
2.
Very good. I'm impressed. That's one kind in that CH3. Very good. And this is another kind. Very good. From ethanol, how many sp3ch stretches should you expect to see in the IR spectrum?
Three.
Anybody wants to share any insight? Not insight. There are two kinds of CHs. That's one kind, the purple. If you can see the color in the propeller of the Cessna, the 3 CHs, they're spinning. Remember, carbon-carbon single bonds can spin. So there is no difference between that bond and that bond and that bond. They're looking like identical springs. They're looking like 3 identical springs. Over here, then you have the carbon-carbon bond. Then you have these springs. Then you have something weird going on here. And then you have another spring like that. If you would use like different types of springs to make a model of ethanol, this is what it's going to look like. So that's a CH, 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 CH. If you see that now in this model using springs, how many CH stretch frequencies or absorption should you expect to see in the IR spectrum of this molecule? 1, 2, 3, 4. Pick a number. Pick your. How many types of CH?
2.
Sorry?
2.
2. One for that and one for that. These two are identical. So whether this guy is going to stretch at 30, 29, 29, 80, if this is absorbing at, I'm just picking a random number, 29, 80 centimeter inverse, this is going to absorb at 29, 80 centimeter inverse. And they're going to fall one on top of the other. It's just going to increase the intensity. not this way, sorry, like an icicle. If this is absorbing at, I don't know, 2945 centimeter inverse, that's going to be true for that, and that. Make sense? Let's keep moving. 312, 412. Sorry. Okay. So that's that, right? So sp3ch, if you have a whole bunch of them, you might see like bunch of peaks. So don't expect a nice clean peak in your molecule when you actually see an IR spectrum. So life is not beautiful most of the time. It's pretty ugly. Okay. sp3ch. When you have an sp3ch, something like this. Carbon, carbon, a double bond. I don't know what else is going on in the other side. I'm not going to bother about it, but let's say there is a hydrogen here. And you have other things attached. It could be another carbon, it could be another cyclic ring, who knows what. This guy is sp2ch. That's what I mean. That's what you should be seeing when you hear something or you read something. It should flash a picture in your brain. Okay, and the picture should look like this: a double bond and a CH at the end of the double bond. That's what it means by sp2ch. Okay, sp3ch. sp3ch is sp3ch, no double bond, no triple bond, a double bond. Okay, this guy shows up little more than 3000 centimeter inverse, probably, not probably, sharp, very sharp, and moderate to intense or weak to intense. I'm going to just say moderate to intense. Okay, usually they're moderate or very weak. Okay, all right. Now the last one in this series is SPCH. Sounds like an animal care facility. SPCH. When you have SPCH, it's over 3000 centimeter inverse, but little more over. Usually it's around, I'm going to use this alternating current sign, around 3300 centimeter inverse. You see, every time I write a range or a number, I always put the centimeter inverse. So if you do not put the centimeter inverse, you will be penalized. So don't do that. Okay. Again, sharp, and this one actually could be pretty intense. If this is going to be more like a weak peak, then this is going to be definitely a moderate to intense peak. Okay, so these are the three carbon hydrogen stretches. Carbon stretches, I don't care. I mean, I don't usually talk a lot about it. I think we will talk about it when we go through the presentation. If I share the presentation very briefly today. Okay, let's now go to one CC bond that's very distinct. Okay, that CC bond is, I'm not going to talk much about single bond carbon bond, or double bond like sp2c, sp2c. But what I really like, which is very distinct, is triple bonds. Okay, so the triple bond could be something like that. There could be another triple bond. This is an alkynyl group or a cyano group or nitride. This is called a nitride. Okay. You have worn nitrile gloves. I don't have any gloves in my office because it's supposed to be a clean area. Nitrile gloves are actually polymers of some sort of cyano groups. It's also called cyano. Cyano group. Okay. Potassium cyanide is KCN. That's an ionic bond. Cn minus and potassium plus. This is very distinct. If this is symmetrical, we read it in the PDF, in the presentation. When a molecule is very symmetrical, it's very difficult for us to get a good IR spectrum. The molecule must have some sort of polarized polarized behavior, polarized property. Okay, if it is symmetrical, then everything is getting canceled out. It's very symmetrical, right? Left and right are pulling with equal strength, so that doesn't really help much with IR spectroscopy. The molecule must be unsymmetric to get a good spectrum. So if you have a molecule that looks like this, you may not get a good IR spectrum. You might be thinking that, oh my God, what did I do? Didn't I synthesize the compound? And then your advisor says, Dr. Mohalski or Dr. Chen says, just relax, it's okay, no problem. It's a very symmetrical molecule. So IR will be, not so good, not good. It's in the PowerPoint or the PDF presentation. So when you have a dissymmetric alkynyl group, or a nitrile itself is dissymmetric, so you don't have to worry about it. It has a very distinct range and a distinct place. Nothing else. Well, I take it back. Almost nothing else shows up there. This guy usually shows up between 2300, 2000 to 2300 centimeter inverse. Okay, sharp and weak. You better be lucky to see it well. It's going to be weak. W means weak. It's going to be a tiny peak over here. Okay. What I'm going to do is I'm going to start erasing all this stuff and start showing you like how that might look like. Okay. That's that. Okay. So we are moving toward this direction. Then what comes as a very beautiful peak is anything carbonyl. If you have a carbonyl group, okay, if you have a carbonyl attached to something, the carbonyl could be part of a ketone. Carbonyl could be part of an aldehyde. Carbonyl could be an acid, anhydride, amide, whatever it is. They vary a little bit. I'm not going to bother you with those little variations. All I want you to know is that any carbonyl shows up between 1600 to 1800 centimeter inverse. Intense, sharp, and intense. I'm going to write down the whole word, intense. You can't miss it. If you have a carbonyl and if you say, oh, my IR doesn't show the carbonyl, you have done something wrong. Okay. So if you have a carbonyl, it's going to show up. Carbonyl is awesome. You can see it like a huge icicle, the longest icicle hanging off of your window frame. Okay. Important. If you have a carbon single bond oxygen, okay, I'm going to draw it this. Let me move this guy a little bit there. It's too crowded. So whatever you have on the sides, let's put the 400 centimeter inverse here. Okay. If you have a single bond carbon oxygen bond, whatever this is, it could be part of an ester, it could be part of an anhydride, it could be part of an carboxylic acid. This one, that's a carbon single bonded oxygen, that carbon single bonded oxygen. If you have a single bonded CO bond, then this guy generally shows up in between 1000 to 1200 centimeter inverse, sharp, moderate to intense. Okay. Next, something that there is no way you can miss. Hydroxide. No way you can miss it. If you have an OH, unless it is hindered, you have to be really unlucky to have a hindered OH, where the OH group is buried under other carbon stuff that it cannot behave like a carbonyl an OH group. I had situations like that. My students have had situations like that in this department, in our research project, okay? And we couldn't see a peak that's very distinguished peak that you cannot miss. OH peak, when you have an OH peak, it's usually 3,200 to 3,600 centimeter inverse, very distinct. It is not sharp. It is very broad. Broad and intense. Okay? Primary, secondary, tertiary, doesn't matter. As long as the hydroxide group is kind of open out in the air, it's going to be very distinct. When you have an NHP, okay, when you have an NHP, it's also very much like the hydroxide peak, but little different. So usually it shows up 3,300 to maybe 3,500. These numbers vary a lot. Centimeter inverse. It's also broad, okay, not that broad. It's also broad, pretty broad. And it's pretty well moderate to intense. I would say, well, more in the intense way, moderate to intense. Okay. When you have a primary, I'm just going to write a little note. It's also in the presentation. So I think you should not completely depend on what we are doing on the board. You should also pay attention to the PDF that I have uploaded. Okay. When it's primary, I mean, like wherever we do it, we're going to look at some of the spectrum. When it's a primary amine, then usually you look like you get two peaks. You get two peaks. This is important. Okay. And there are probably like few other important peaks that I have forgotten. Okay. I have also uploaded a list of infrared absorption, like a list of different absorption numbers for different things, different functional groups. It's called IR absorption list or something. I don't remember what it is. Okay, so let's stare at the board maybe for 30 seconds. I'm gonna keep my mouth shut. Then maybe I'll show you like how the peaks look like, and then what we're gonna do is we're gonna go back to the presentation, and especially the weight presentation, the one that has mass spec along with it. So we're going to go through that, and I'm going to show you like few spectrum and show you like what they look like. Okay. So take a look at it. This is nothing but a laundry list. You should probably, I hate to say that I want you guys to memorize it. You should probably like see them enough in the spectra, practice enough problems, work out the homework problems. Maybe this is something that you should be reading the book, not just entirely depend on my lecture. So you should see them enough so that these numbers start sticking to your brain. You know where they show up. Okay, there are not too many. You should get pretty familiarized with it. Not necessarily memorize. I don't like to use the word memorize. Okay, you should see it so many times that it just eventually becomes your second nature. Okay. All right. So let's pause for a couple of maybe a minute. I should probably take a picture of the board just in case I erase something important. Hold on. Excuse me. I'm blocking the camera again. Okay. Got it. I'll try to keep my mouth shut for a few seconds. I don't think there is much to discuss here. What do we discuss? Like, why is it 3,300? Because it's a tough spring. Tough life, son. I'm just kidding. Okay, so let me show you like what they might look like. So if you see, let's do some mock molecules. Let's pretend that we are seeing the spectrum. Okay. Okay, maybe what we can do is we can be clever. We can use different colors, maybe 4 or 5 colors for drawing 4 or 5 molecules, laying one on top of the other. That'll be pretty cool. Okay, let's start with the black color. Let's draw like an alkane. Let's say we have I don't know, what's your favorite alkane? Don't go beyond 10. What's your favorite alkane? If you have a puppy and if you are forced to name the puppy by the name of an alkane starting from carbon 1 to carbon 10, what would you name your puppy?
Octane.
Octane. All right. This is your dog. That looks like a rabbit. That's octane. One, two, three, four, five, six, seven, eight. Let me ask you a symmetrical question. Shall I? Jokes apart. Let's be serious. Let me just draw this molecule big. Is it octane? 1, 2, 3, 4, 5, 6, 7, 8. Oops, that's not in. How many kinds of CHs are there? It's only sp3ch, right? There is no double bond, there is no single bond. All these carbons are sp3. How many kinds of CHs are present? CH. How many kinds of CH single bond are present in this molecule? Let's see how many of you can actually explain that.
2.
Yeah, 2 is like this.
2 is wrong. How many kinds? You know what? I think I should help you.
I'm gonna say 4.
Eleanor,
Yes.
you said 4.
Yeah.
Why? Okay. Keep quiet for a few seconds.
Okay.
Anybody else? I heard 2 and 4.
Wait, can you repeat the question again? Just
How many kinds of CH bonds are present in octane? That's a CH, right? Methyl. That's a methyl. We are not showing the hydrogens. That's a CH, that's a CH, that's a CH, that's a CH, CH, CH. I'm exercising my right wrist. Actually, I hurt my wrist many months ago. It still hurts. So there's a CH3, there is a CH2, there is a CH2, CH2. Some of the CH2s may be equivalent to the other CH2. The 2 methyls at the 2 ends may be same based on symmetry. You really need to get down with symmetry. You need to really understand, because when we start talking about NMR, symmetry plays a significant role. So I'm saying there are 3 CHs, 2 CHs, so 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There are 18 carbons, 18 hydrogens, and 18 CH bonds present. Some of them are equivalent. So if they're equivalent, all of them are equivalent, there is only one kind of CH. Or if there are 2 kinds, there are 2 kinds. How many kinds of CH are present in this molecule? One answer is 2, one answer is 4.
3.
Okay, we heard 2, 3, 4. This is a good time to, even though it's not directly related to infrared spectroscopy, but this is the right time to discuss symmetries, because spectroscopy is it's imperative that you understand symmetry when we talk about spectroscopy. NMR is mostly NMR, not so much IR, but I think it's important that we understand. Okay, so I'm going to put different shapes in different colors around these carbons to show that they are symmetrical or not. Okay, so let me put a rectangle here that covers these three CHs. Okay, the methyl group at the left end of octane, the propeller at the end, right? Like a little flower with three petals. Those three CHs, is that same or identical with another CH3 or something else in the molecule, or they are unique? Anybody wants to take that question and kind of articulate the answer? Is there something else, another body part that's identical to that, property-wise? Anybody can answer.
The one on the other end, the 8th carbon.
One on the other end. Okay. So, Eleanor, you think that there's, am I butchering your name?
No, you got it.
Are you being polite?
No, it's Eleanor.
Nothing is silent or anything, right? Eleanor or Elio. Okay.
I go by whatever, as long as it starts with L.
That's great. Okay, that's very kind of you. Okay, now I'm going to put like a different shape. This CH2, is there another CH2 that's like that CH2? This one? Yes or no?
Yes, 7 carbon.
When you look at a molecule, why am I looking beyond? I have everything right here. I totally forgot about it. Hold on just a second. I have my models. What is wrong with me? Oh, something is running away from me that doesn't like me. Yeah, hold on. Just give me a second. I'm just setting up my model. It's a little mess here right now. Okay. One, two, three, four, five. I need a few more. Almost there. I think we got an octane finally. 1, 2, 3, 4, 5, 6, 7. Oh, one more. Do I have this connector? Okay, there you go. I finally found it. This little thing that connects the two sticks. Okay, I think we finally got octane. One, can you see pretty much the whole thing here? 1, 2, 3, 4, 5, 6, 7, 8. Octane, right? There is a CH3 here. We are not showing it. CH2, 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 CH2. Right? So when you look at this molecule, okay, this molecule has a symmetry in the middle. Carbon 1, 2, 3, 4, 5, 6, 7, 8. So the molecule is symmetric from the middle. Okay, the top half and the bottom half are pretty much the same because they're both butyl chains. This is CH2, 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 CH3, and this is also CH2, 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 CH3. It's like the same thing. These two identical pieces attached with each other with a CC bond. Pretty much like this. If you look at it this way, I think it'll make more sense. This is exactly what I was looking for. If I put it this way, it'll make more sense to you. Now you can see the symmetry, right? If it would behave. Okay. You can see that these two are identical. right? This CH2 and this CH2, they look pretty much the same. If you now look at the molecule, right side and the left side is nothing but a mirror image or reflection of the right side. You have studied stereochemistry, right? So you can tell that the methyl groups, as Eleanor said, they're identical. These two guys, number 2 and number 7 are identical. Number 3 and number 6 are identical. And number 4 and number 5 are identical. So how many kinds of CHs are there? 1, 2, 3, 4. Make sense?
Yes.
It's probably not that critical for this IR discussion, but we will get back to the symmetry when we talk about NMR. Okay, so let me just put those signs. These CH2s are identical. The methyls are identical. These CH2s are identical. And these are identical. So ideally, if you have octane, okay, for the CH stretching frequencies, where should you see the CH stretching frequency in the spectrum? Look at the laundry list and tell me, where should I draw the peak or peaks? Should I draw them in between 1600 and 1800 here, a broad peak here, or where should I draw them? It's sp3ch. Look at the list and tell me, where should that peak, the absorption happen?
3,000 centimeters in
Less than 3,000 or more than 3,000?
more than.
Less or more? I could hear you.
More.
This means less than 3,000. Okay, so it should be if this is the 3,000 mark, if this is 3,000, when you take an IR spectrum of this molecule, should the peaks be on the right side or the left side of the green mark?
On the right side.
Okay, ideally, you should see 4 peaks. It's not going to be that pretty, okay? It's not going to be 4 peaks because they're going to overlap and it's going to look like a little mushed up, like a little hibby-jibby, okay? It's going to be very difficult to see what's going on. One of them might be a taller peak. Who knows? I don't know. Something like that, okay? So that's that, okay? Let's draw another molecule. So that this is how an octane will look like. And it'll have its CC peaks over here. Don't ask me how it's going to look like. Okay, we can cheat by looking at a real spectrum. I have no idea. It'll probably show up somewhere here or here in the fingerprint region. Yeah. All right, let's draw another molecule. We have 5 more minutes. Let's draw an alcohol. Let's draw our favorite alcohol. Okay. A typical question that I might ask you is write down the infrared frequency stretching ranges, the important stretching ranges for the following molecule. Like if you see a molecule, if you take ethanol and if you take its infrared spectrum, which peaks are going to be standing out that we have covered in our lecture? Which peaks you think you can talk about from your learning in this class? Okay, let's start from this end. What kind of peak will this molecule, you know what, let's make this molecule green because this is all black, okay? This is all black, this is all green. So we're going to designate the molecules by their color. So if you see an ethanol molecule, what kind of stretching frequencies this molecule is going to be absorbing infrared radiation? What kind of bond is here? It's a CH3 and a CH2.
It'll be a sp3ch.
It's going to be sp3ch. Where would that sp3ch show up in the IR spectrum?
Less than
3,000 centimeter inverse, right? Let's say, I'm just going to overwrite it. Let's say it's going to be here. Okay, what else is there in this molecule that's going to be very significant in this molecule?
Definitely the OH.
OH. That's going to be the OH. Something else we have discussed.
The CO bond
CO bond, where will that show up?
from 1000 to 1200 centimeter inverse.
That's going to be the infrared spectrum of that molecule. Mind you, if you really pull the IR spectrum of ethanol, it'll probably have many more peaks. These are all stretching frequencies. Remember that the CHs can do this. All these movements, they're all bending frequencies. When the springs are bending, they're also absorbing a different range of infrared radiation. And they're going to be showing up somewhere here in the fingerprint region. I have no idea where they will show up, okay? So forgive me for my ignorance. Okay, you have to, we have no other choice. That's that. Okay, all right, let's go with another one. Another known molecule that we have seen. Nail polish remover. Okay, I'm going to draw everything in red. Okay, which two significant infrared stretches you can think about that acetone will show in its infrared spectrum? Two specific peaks that you cannot miss. Even you are being taught by me, who is pretty sketchy with its IR knowledge. Which two frequencies will be distinct for acetone? Let's start from here. Will you see something in this region?
The sp2 CH.
sp2? What's the is that sp2 or sp3?
sp3, sorry about that.
No, that's fine. That's totally fine. That's totally fine. sp3ch. Where will it show up? Where will these 6 ch absorption stretching frequencies show up?
Less than 3000 centimeters inverse.
So let's say they show up here. Okay. Another very significant peak. There is no way you can miss it. Where will that show up? Carbonyl.
16 to 1800.
It's literally going to look like that. Okay, let's do another one. If you have a molecule, let's use purple. The purple molecule with a triple bond. Let's start with this molecule. How many peaks can you think about, legitimate peaks that will show up somewhere in this molecule? Let's start here on the extreme left. What kind of CHs are these? sp3,
sp3,
sp2, or sp?
sp3.
Okay, I'm going to just move this guy a little bit to the right. It's there. What else? The CH. What kind of CH is that?
SP.
SP.
Where will that show up?
Around 3300 centimeters inverse.
And is it a symmetric molecule or an unsymmetric molecule? Is this triple bond symmetric or not? It's not, because you've got a methyl group on this side and a hydrogen on the other side. It's not symmetric, so it's good. It will probably be pretty IR active. Where will that show up?
$2,000 to $2,300.
We are past the time. So I'm going to take a snapshot, make the video and the still pictures available. I want you guys to go through the PDFs of the both PowerPoint PDFs and familiarize yourselves with the different types of IR spectra. Okay, different molecules, and you will get a kick out of it. One interesting thing is when you have a carboxylic acid, for carboxylic acid, the OH is even wider. It starts from 2500. It's a huge beehive hanging from the roof. Okay, when it's a carboxylic acid. Remember that carboxylic acid has that and this. Okay, so it's got two very important groups, the hydroxide that shows up here and the carbonyl that shows up here, and then you have the CO bond. Okay, three distinct peaks. So this is going to be 1600 to 1800 centimeter inverse. This is going to be 1000 to 1200 centimeter inverse. And this particular OH, because it's in a very special environment, it's going to be a weird one, 2500 to 3700 centimeter inverse. It's extremely broad, and it's going to start from here, 2500, slowly come down like a huge, like a huge beehive. Okay, I'm going to take a snapshot, and this is pretty much it. So you guys study and have some fun, and then we're going to see you guys on when? Tuesday. Hi, Matthew. I see you on the screen. You have a very fancy microphone. Are you a DJ or you have your own show or something?
No, I got it for Christmas. It was just a mic so I could actually talk.
Cool. Must be a really fancy one. Are you into electronics?
A little bit, not too much.
Cool. All right, everybody, have a good weekend. I'm going to not forget to take a snapshot. I think I might have forgotten to take a picture earlier. Somebody asked me and I don't have it. Okay, have a good weekend, guys. Take care and get some rest. Don't get into trouble. Don't touch anyone who has COVID-19. Or don't give it to anyone. Okay, bye.